In this video, we will be discussing physical properties, chemical properties, physical changes, and chemical changes. The learning objective for this video is to learn to recognize physical and chemical changes and properties. We will start off by figuring out the physical properties. Physical properties are properties that can be observed without changing the matter's composition. For instance, the color of a substance, the density, the state of matter, boiling point, and freezing point. Boiling point means the temperature it boils, and freezing point means the temperature that it freezes at, or that it melts at. And so freezing for water happens at 0 degrees Celsius. And so we can record that this is solid water, this is liquidy water. So we can record the states of matter, we can record that it's clear, and all of that doesn't change the fact that it is water. So all of those properties are physical properties of the substance. Physical changes are processes or changes that occur to matter that do not change its overall composition. For instance, cutting a piece of paper just makes it into smaller pieces of paper. It doesn't change the fact that it's paper. So mowing the lawn, cutting the paper, those are physical changes. Also, distillation is a physical change, and filtering are physical changes because those do not change the composition. Those are just ways of separating mixtures. And so mixtures can be separated by physical changes, such as filtering or distillation. Now, what's happening during a physical change at the submicroscopic level? So let's take water, for instance. We can fill an ice cube tray with water from the tap, put it in the freezer, and then it changes from liquid to solid. It's still water, though. So on the submicroscopic level, what's different between liquid water and solid water? So liquid water, our molecules of water are able to move past one another. They are free flowing. And so they're not organized, they're very close together, but they are able to move past one another. In this solid water, our water molecules have tried to line up to lower their potential energy. And so we get this nice crystalline arrangement that we know as ice. But you can see that even ice is still made up of molecules that are still H2O. And so each building block here is still H2O, meaning 2 hydrogens and 1 oxygen. So in both cases, it is H2O before the change and H2O after the change. And so this physical change did not change the fact that each molecule is H2O. It just changed how they're arranged to one another. So if we were going to represent this with symbolic language, we would represent this side of the as H2O liquid, and then it's changed into H2O that's a solid. And so what did you start off with and what did it change into? And so the only difference here is not to the chemical formula, but just to the state of matter. As I said before, mixtures can be separated by physical processes. And so mixtures really take into account that all of the components in the mixture have different physical properties. And so that could be differences in boiling point, differences in state of matter, differences in how they stick to different surfaces, density, or volatility. And so because of these differences, we can use different techniques in order to separate mixtures based on that different property. So if they have different boiling points, we can distill the substances. That means boil off the lower melting point or lower boiling point substance and collecting it in another flask. We can also filter substances, because if you have solids and you have liquids, you can filter and separate the solid from the liquid. So if you had a mixture of sand and water, you could filter it to separate the liquid water from the solid sand. Chromatography is another technique for separating substances based on how well they stick to a substrate. And then you can also evaporate substances or separate things based on their density. Mixtures can be separated by physical processes, but pure substances cannot. A pure substance cannot be broken down into its component elements based on a physical change. To break a pure substance down into its component elements, that requires a chemical reaction, a chemical change. Chemical properties refer to properties that can be observed only when we're changing a matter's composition. So that it's like how flammable something is, how acidic something is, or how toxic something is. Those have to relate to how those molecules participate in chemical reactions. And so how do they change in patterns and how they change relate to its chemical properties. And so iron rusting here is an example of a chemical property because it's showing how it reacts to water, particularly acidy water that it's exposed to. Chemical changes are processes that change the matter's composition into something completely new and completely different. So before I showed the example of cutting paper, in a chemical change, that's like burning paper. Burning, rusting, and aerobic respiration are all examples of chemical changes. We know that you breathe in O2, so humans breathe in O2, and breathe out CO2. And so we are constantly changing the composition of molecules when we breathe. Plants do the opposite in photosynthesis, and so they take in CO2 and put out O2 gas in photosynthesis. When you burn paper, you produce CO2 and H2O, and this is cellulose, which is a polymer of glucose, which is C6H12O6. So chains of glucose make up cellulose, and so when we burn it, you get carbon dioxide and water. There's other components in here, but it's all hydrocarbons, and so it's all going to burn into CO2 and H2O. But the bottom line is you're turning it into something completely different. When you burn, you're also reacting with O2. So chemical changes that are occurring. You're making something new. So when you're doing chemical change on a microscopic level, sometimes you can tell with your eyeballs what's happening, and sometimes you have to use your other senses. And so for this example, it's taking colorless gases that have no smell and producing a colorless gas that actually has a smell. But if we look at the original mixture here, this molecule is N2, this molecule is H2, 2 hydrogens, 2 nitrogens in those respective molecules. And then after this chemical change, this substance here, this molecule, consists of 1 nitrogen and 3 hydrogens. And so each molecule here represents ammonia, NH3, and then this is nitrogen gas and hydrogen gas. In symbolic language, we would represent this chemical change as N2 nitrogen gas reacting with 3 hydrogen gas molecules in order to produce 2 ammonia molecules. I recognize that there are 4 ammonias in the picture, but we always put these numbers up in front for the lowest whole number possible. And so the 2 and the 4 and the 6 would simplify from 2, 6, and 4 down to 1, 3, and 2. It's always lowest whole number in the symbolic language. More on that in a future chapter. What's important to recognize is that the physical and chemical properties of the pure elements that make up a compound are completely different and completely unrelated to the physical and chemical properties that make up the compound. Pure elemental sodium, for instance, is a metal that catches on fire when we put this into water. Chlorine gas is a diatomic gas that is toxic at fairly low concentrations. Once the sodium and the chlorine react together, though, they make an ionic compound known as sodium chloride that is completely edible. We put that on food. It's known as table salt. You probably have some on your kitchen table or on your kitchen counter or in a kitchen cabinet. It is yummy. It's good. Just don't eat too much of it because it's not good for your heart health. But that's different. The point is that the properties of this sodium chloride are completely different from the properties of the pure sodium or pure chlorine. Now, according to our law of conservation of matter, matter cannot be created nor destroyed in a chemical change or in a physical change. Matter cannot be created nor destroyed. So that's important to recognize because when we're changing matter, we are not actually changing how much matter there is. The amount of matter before is equal to the amount of matter after. So when we burn paper, we don't destroy that mass and turn it into energy. We are just converting from all the carbon atoms and oxygen and hydrogen that were in the paper and converting them into different substances, but we have the same number of atoms after than we did before. And so in this picture, you can see a lead battery, and as the battery produces power, the substances in the battery change, but the mass of the battery is the same. The battery doesn't weigh less all of a sudden. It's the same amount before and after. Now, when we lose weight, like through dieting and exercise, where does our lost mass go? Because we know from the conservation of matter that we can't destroy that matter. Whatever mass we lost has to still exist. So where did it go? Well, when we lose body mass, we are losing body mass through carbon dioxide breathing because we breathe in O2 and CO2 is breathed out. That's an additional carbon atom tacked on to that molecule. So every breath we are losing mass through carbon atoms. And so when we exercise, remember to breathe because that's part of your weight loss. Also, that process that makes the CO2 also produces H2O, and so that is lost. Water is lost through sweat and through urine. But when you lose weight, it's not like you're burning fat into energy. You are burning fat into carbon dioxide and water. Energy is just a byproduct that our body makes use of. But mass is not created nor destroyed in a chemical or physical change.